With a small audience, I guess I can ask how many folks are, what can I say, in agreement with the idea of the Big Bang? When I was first introduced to the idea of the Big Bang, I imagined that there was one place in the universe that just exploded with all this energy and filled the universe. And since then, I've changed my view due to some other things that I've read and encountered. And the idea is that, first of all, the Big Bang happened everywhere, not just in one place. It's like taking a bottle of champagne or a bottle of soda water and opening it, and all of the bubbles come out at once. So there's not just one universe, in a sense. There are many. And they may not even be adjacent to or interact with each other. Hopefully they don't, or we wouldn't be here. So if one of these bubbles expands too fast, then we would never have existed. Things would have gone through their whole process without giving life the chance to, arise. If it had gone too slow, same thing, for a different reason. So we're here, at least from that first instance, because our universe expanded just right. Now, as it cools, first of all, I don't think you would see light. The energy is too high. If you saw electromagnetic energy of very high energy, not only would it chew your bones to bits, it would chew your DNA to bits, or at least knock out important parts of it, and you'd come out all kinds of ways. So for life to form at all, we had to live in a place where the energies were just about right. And so around every medium-sized sun, they say there's a biotic zone. And if your planet just happens to be in that biotic zone, then your chances of emerging are pretty good. So what about dispensing with that miracle, going to the next? I call them miracles because they always boggle my mind when I think about them. What about the whole thing about birth itself?
About what?
Birth itself.
Birth?
Birth. From, from egg and sperm, and you're a choice. Every one of you and me, we're a choice. The egg chooses. All these sperm come in, there's millions, lots of them, and the egg allows one, and it's all over. So, but we all got chosen right away, right? And then when you go through your developmental stage, this eye-brain connection thing kicks in such a way, very slowly, that you may be able, I'd say by the second trimester, you may be able to detect light through the placenta, probably in the redder parts of the spectrum, so that here again, the number of things that can happen to us when we're in development is that go awry are really quite overwhelming, I think. So when you come on, if you're here, come on in and take a seat. And we're
Front rows for geniuses.
Yeah, these are all the invisible folks. By the way, the newest thing in light is that, and this was just recently, that they can now, on a very small scale, make light go around an object as if the object weren't there, and it doesn't interfere with the light at all. And so they're now using light to make things invisible.
Well, if it goes around, then it is being interfered with.
Well,
In the net result.
but it comes, they bring it back together, so the net result is that you don't notice that it has gone around something. Yeah. And that was just recent.
I missed your first talk, but did you talk about the nature of light and the light spectrum? And
Yeah, I'm free form here, and if you want to go through the nature of light.
Well, I'm very curious about it because of the spectrum, like.
Okay, so.
I mean, light. Why are microwaves and radio part of the spectrum? Why is it also referred to as electromagnetic energy? Why is it bendable by gravity if it doesn't have any mass? Those kinds of things.
You must be a happy man.
Why?
Exactly. You ask why a lot, and. which means there's curiosity, there's involvement with the world around you, there's all of this stuff, right? So how far back you want to go? Let's go back to.
Well, you started with the Big Bang, but you know the thing about the Big Bang is.
5 billion years.
We don't know where the center of the universe is. So how can we prove today?
And how many or none of that, right? And it always amuses me when I watch the TV programs and they show me the Big Bang explosion, as if they were sitting on the 50-yard line of watching the football game, right? They're making all this up, right? So it sounds flippant to say we're making it up, but we're very careful about how we make things up, and we have some criteria. Things have to be consistent. We believe in consistency, right? And then something comes along that isn't consistent with what we think about or have figured out, and as soon as that comes along, we reevaluate what we've done before and we try to incorporate it. So there's all of this part going on, which is really critical to understanding more and more. If I were talking 500 years ago, nothing like this would come out. And so think about 500 years from now. Everything I'm going to say is what? Erroneous. And I think when you're in school and if you're really thinking about who's your authority, you know, where's your truth? Is it the textbook? Is it the teacher? Is it somebody has letters after their name, like, you know, PhD and all that? What? Okay? So 2,500 years ago, I'm a Greek. Okay? And as a Greek, I'm here to tell you that the only way I see something is for the light to come from my eyes. It comes from my eyes, it hits you, and it comes back to me, and I interpret it. Now, when somebody says to me, well, how come I can see the stars in the dark? You know, they're far away. You know, it leaves your eye and goes, oh, light, infinite speed. It happens instantaneously. There's no time for light to travel, right? Now, some folks took issue with that, but it was a popular notion, and the folks that took issue didn't get much credit. Okay, so, but we still have it in our language. It's amazing how we preserve things in language. Things like the light went out of his eyes. If somebody is depressed or bored, it's like, oh, you know, the light's gone out of their eyes. Or cast your gaze, which is a little archaic, but, you know. So that went on for a long time, up until about 500 years ago. And 500 years ago, in the Renaissance, folks started experimenting and looking at things, and they came to the conclusion, they came to two different conclusions. One was that light was a particle because you have sharp edges and you shine light that way and you get a shadow. And so, you know, this is the way light travels, and so it must be particles. Some folks thought, well, you know, I'm looking at water and I see how water moves and I see how things happen, and maybe they even look through the little cracks in their fingers. And when you look through if you take your fingers and put them together real tight, you'll see light coming through one little space. Well, take that little space right up to your eye, and if light travels in straight lines, you'll see two distinct lines, one of one finger, one of the other finger, but you don't see that. You bring it right up to your eye like this, and you see a lot of little, looks like hairs in between your fingers. Well, what's that? It's not really hairs. If you look at a fluorescent light and you line up the fluorescent light in there, you'll see these little bands, these little dark bands. Well, thing is, that's the only way you can explain that is to explain light as a wave. So in early 1600s, you had two camps. One says light's a wave, one says light's a particle. The guy that was saying light was a particle, Isaac Newton, also had some other physics, and he figures all physics ought to fit together. So here comes a particle of light. And the particle of light is traveling in this direction. Now he's already made up something. And he made up that an object will travel in a right straight line unless it is affected by a force. And if you affect something by a force, that something is going to speed up. So here comes the particle in a right straight line, and there's a boundary. Over here's air, over there's glass, and I'm coming into the glass, and I go this way, right? If you care to see that, I got a bunch of little blocks here, and take a block and look through the block like this, and then stick your other finger up so that your finger is, and you know, you're looking at your finger straight on, and you see the finger outside the block and the finger inside the block, right? Now, without moving your finger, twist the block. What happens to the finger?
It bends a little bit.
It moves over, right? So what that means is the light, when it goes through that plastic, is actually taking a different direction, right? So here comes the light, comes to the plastic, hits the plastic, takes a different direction, and Newton says the only way it can take that different direction is it goes faster in there than it does out here. He shot himself in the foot. He tried his best to make it fit the physics he had, and he says light travels faster in water and glass than it does in air. Well, Newton was famous, he did a lot of great things, and he was popular, and this was a time when countries were fighting like you did over football teams. Our scientists are better than your scientists. Gee, look what we've done, you haven't done nearly so much. England was very active in science at the time, and Newton took precedence, and for what, 200 years? For 200 years, people thought light traveled faster in material than it did in air because they couldn't test it. So 200 years later, when they test it and they find out that light travels slower in material than it does in no material, then they had to revise and change from the particle idea to the wave idea, because a wave, when a wave is coming in on a boundary like this, and when the wave front hits the boundary, this part slows down. And this part keeps on going. And as it hits the boundary, each part slows down and it naturally bends inward. So it's like, oh, we know it slows down. Again, we're trying to make things fit. Everything has to be consistent, blah, blah, blah. And that held for, until, let's say, 1900. Now, in the meantime, people studying heat were sneaking up on the people who were studying light. And the people who were studying light, James Clerk Maxwell for one, and Michael Faraday, came to the conclusion that, okay, light is a wave. We know that it has a definite speed. We know it has a different speed in air than it does in glass. And Maxwell was a mathematician, so he made, keep in mind, particle is a model, wave is a model. We don't know what light is. We thought we did, but today we don't. And Maxwell was actually studying electromagnetic radiation as well as light, and came to the conclusion that electromagnetic radiation travels at 3 times 10 to the 8th meters per second, and approximately, and light travels the same speed, so light must be electromagnetically related. He didn't know anything about electrons. He didn't know anything about, well, people had proposed atoms, but a lot of scientists didn't believe in them at the time. So, you know, it was that kind of a thing. But the people that were studying heat, we now call them thermodynamicists, I guess. I don't know what to call them. They study thermodynamics. We're doing experiments on things they call black body radiation. Now this is a total, it goes against any thinking that you might, any sensible thinking you might do. The sun is a black body. The moon is not a black body. If you heat up something and the light that is coming off of it comes from just that thing itself, not from any reflection, not from anything else, it's a black body. Because it's whatever light you measure coming from it, that's all the light there is. So they were figuring out equations for black body radiation and all this sort of thing. And they also had another mysterious thing happening, and that was that they could, this was after they discovered electrons, they could shine light on certain material and kick off electrons. If you took, some of you know what an electroscope is. If you take, 2 pieces of plastic and you rub them in your fingers like this, they'll separate. They get statically charged. So if you have those little pieces of plastic or metal or whatever connected to a zinc disc, and then you shine light on the zinc disc, those things will collapse, which means that light is knocking off electrons. Now we're in trouble again, okay? Because we're in trouble again because Newton has established that if I take, I have a bowl full of particles here that I don't know who put them here, but I'm so pleased they're there. If I take one particle and I hit this particle with this particle, this will gain momentum. It'll gain velocity. So I have this notion. Conservation of momentum, conservation of energy. These are the 2 big chiseled in stone things in science, right? So here I'm stuck with this. Light can kick out electrons. I'm in a quandary again. Because light is supposed to have no mass. And if you don't have any mass, you can't transfer momentum. So we have to say, okay, it has no mass, but it transfers momentum. Okay, we're looking for consistency. What does that do to classical mechanics? That kicks it in the head, right? So, so there's still a lot of trouble over what is it, right? Well, Einstein got his only Nobel Prize, not for relativity. He got his only Nobel Prize for photoelectric effect. Well, maybe he got another one for Brownian motion, I'm not sure.
He just got one.
Huh?
He just got one.
He just got one? It was for photoelectric effect, where he proposed that light was truly a particle that could actually kick out electrons. And so he established that, okay, it acts like a particle. So they came along to George Gamow wrote a book called 30 Years That Shook Physics. It went from 1900 to about 1930. Physics was a mess. They couldn't really figure things out. Niels Bohr, one of the originators of atomic theory, is quoted as having said, if he had known that physics was going to be this way when he had studied it at the university, he would have become a circus clown. Because it didn't make sense. You know, it's a particle, it's a wave. It's a particle that waves. Well, maybe it's a wave of particles. Maybe it's a particle on Monday, Wednesday, Friday. Maybe it's a wave on Tuesday and Thursday. And pretty soon you come to the notion that if you interact with light when it travels, it acts like a wave. If you interact with light when it affects your eyeballs or when it hits metal or anything like that, it acts like a particle. So you soon come to the notion of, I don't know what it is. Can't tell you what it is. But sometimes I can pretend it's a wave and get the right answers. Other times I can pretend it's a particle and get the right answers. But I can't do both.
And the particle is the one that would have mass.
Or transfer momentum. Waves don't transfer momentum.
Be bended by a black hole or sucked in by a black hole. It's because of the particle part,
right,
not the wave part.
Right.
Okay.
And let me throw in this while we're on that particular subject, that is that where's light come from? Okay? We are currently convinced, back in the corner there, if you saw the gas tubes, the glowing gas tubes, those are subjected to about 12,000 volts, AC or DC, it doesn't matter. And what's happening is the electrons in there are being accelerated. The gas that is in there, the electrons in that gas are being energized in increments. They call these increments H frequency. There's a little number, and if you multiply that number times the frequency of the light, assuming it's a wave, right, pretending, then you get a standard number. You cannot have any energy less than that energy. Everything comes in quanta of energy. So you've got, you know, these electrons can only be energized in energy quanta increments, which means in terms of the eyes and in terms of our development, we got accustomed to energies that weren't high enough to chew us to bits and energies that weren't so little that we couldn't detect them, and we developed apparatus for looking within ourselves, of looking and seeing just that small spectrum.
I don't know if you can see or understand the concept of electrons, atoms. Maybe
No, that's way ahead, right? So, guys, forget what light is, forget all the theories, and actually explore to see what light does, right? So what you can do what you can do is you can take a CD, okay, and you look at a CD, have a CD. By the way, this doesn't work as well on what's the other one besides CD?
DVD.
Huh? DVD doesn't work well on DVD. Here, try. I have more. I have a bunch more. Okay. Now, anyone else want a CD? Have a CD.
That's fine.
No, no, please. And if you look at it, go home, get one, go up to the Christmas tree, and look at the Christmas tree in reflection.
Okay.
Or if you're in here, you're going to get a different kind of reflection depending on the number of lights that you see. There you go. I think I've got another one. Nope. Someone needs to loan me one because those don't work. Could I borrow yours for just a minute? Now, in terms of colors and rainbows and things like that, you have to know where to look. If I were to shine this light on that CD, I'd get a reflection of the light over, you know, as angle it's coming in is going to equal angle it goes out, right? Now turn it over and shine the same light on the same thing. Now notice where the spot is reflected to. But then notice the rainbows, right? Notice the colors. Now, how can you explain that? Yes, ma'am.
In white light, it's separated into the entire colors of the rainbow, but you don't see them unless you use a prism or something like that.
But that's not a prism. I have a prism, and I can do it with a prism. You're right. Where is my prism? Oh, those prisms are too complicated for me. I need an uncomplicated prism.
Remember there's a bench.
Where? On the bench? No, that's just, see, the prism has to be a triangular shape, right? And then even with a prism, you need to know where to look. So if you take the prism, I'm really disturbed. I don't see my prisms anymore. Oh well. That's what happens. Here, oh wait. I need to put my, by the way, spectrum, spectator, spectacles. I need to put my spectacles on. So there's a lot of information in words, right? So if I'm playing with a prism and I start turning it around in the light, I soon find out that if I put the point up and I shine the light like this, and then I put my eye over here or a piece of paper over here, I get the spectrum over here, right? Now if I'm watching a rainbow, do you know how to find a rainbow?
Huh? On the ground or somewhere.
Rainbows are really circular. There's no end to them. It's just that the rest of the circle is below ground. The other part of the circle is above ground. Here's what you do. After it rains and it's cloudy in one part of the sky, make sure the sun is right behind your head. You don't look into the sun. You look away from the sun. Look right from the sun to your head to the cloud and go up about 45 degrees and you'll see the rainbow. If the clouds are okay or if they're right. So to see a rainbow you need to, know what's going on with the rainbow. Now, what is this? Have any idea?
Film.
It's film, yeah, it's plastic. What do you see? Here you go. It's all yours. Keep it. You can have it. What do you see? Play with it. You can keep it. If you hold it up to your eye, again, and look at an edge, or look at a light, and sometimes you'll see a red, blue, green reflection to your left or your right. That's the way they're supposed to be looked at. And sometimes you'll see them up and down. So if you look at the window, you can see a rainbow above the window, and you can see a rainbow below the window, right? If you turn it just right. So would you like one for each eye? Like a pair of glasses? There you go. Pair of glasses, pair of glasses. These are different glasses. You can paste these on your glasses. I could put them inside. Here, have two.
Very cool, I recommend it.
There you go. Got two?
It uses this.
Huh?
How does this relate to 3D glasses?
It doesn't.
Okay.
The 3D glasses are more in polarization. You've got one view was taken with a camera with this polarization, one view was taken with another polar, and your brain then puts those two different things together. What this does is it follows the ideas of someone who came after 1930, a man by the name of Richard Feynman. I call him Feynman, some people call him Feynman, F-E-Y-N-M-A-N. And he said, he was the one that first said, forget about what light is. But I have this really neat model. And the neat model is, since light can travel in any direction, it does. Since light can reflect in any direction, it does. Angle of incidence equals angle of reflection is an illusion. If you imagine from the atom where light originates, that it's coming off as a particle, and in that particle is some sort of a repeating vibration or something. He imagines it as a little clock. When it comes off, the little clock hand starts turning. And if the clock from this atom encounters the clock from this atom, when their hands are at just the right place, you'll see that color. This is how the CD works. This is how these work. So the idea is, if I'm looking at the window, I don't see the rainbow on the window. I see an image of the window below and an image of the window above, and the rainbows are reversed. And if I go over and look at those gas tubes, I find out that every element has its own spectra. Every element has its own colors. So 100 years ago, folks would have died to have one of these. I mean, it took enormous technology to take a piece of metal and scratch it and move over a tiny fraction of a millimeter and scratch it again and scratch it so slowly that you didn't roll it up, right? You didn't mess up the metal. It was an amazing thing. And now they have those, and they just paint them with plastic and sell them. You can get great ones now for practically nothing. Pardon? It's called a diffraction grating. And it breaks the light up into its colors much better than a prism, much better than a CD.
This is a plastic material, right?
Mm-hmm. It's just plastic. And it's got little grooves. You know, if you had a microscope and you looked at it, you'd see little lines very, very close together. And the closer together they are, the better it looks. So let me try something here. I have a device that looks like this. That's all it is. It's a slit. I don't know if you can see it, but it's a slit, all right? And by turning this screw, I can shut the slit or open the slit. That's all it is.
Oh.
You can. I have another one.
You said, getting back to something you said earlier about light actually slowing down through objects rather than speeding up.
Mm-hmm.
That means that the speed of light is not necessarily a constant thing?
Now suppose I wanted to say the speed of light is the speed of light. Okay? And I know now that they can actually trap light in certain kinds of atoms, have them just circle the atom. They call it stopping light. I think that's a little arrogant. They don't really stop light. Light continues in a circle and then release it later. So if you can stop it, in other words, direct it into a circular path and then release it later, you can imagine, oh, it must have stopped. It went in. I didn't see it for a long, long time. I made a trigger. It came out. I stopped it. Ha ha. You just made it go in circles, right? So I've got this material, I've got matter, right? And I've got molecule after molecule after molecule after molecule, and there's something about that matter that transmits light. So why are some things opaque? Why is it you can't see through some things, and yet you can see through others? What's the construction there, right? So suppose light comes in, it is absorbed by one of those atoms, spits out the other side, right? Gets absorbed by the next atom, spits out the other side, da 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 da. It's like throwing a ball to somebody at the speed of light, and then they take it and throw it to the next person at the speed of light, and the next, and you have a delay time every time, right? So suppose that in the glass or the water, it goes from molecule to molecule at the speed of light, but in between times, it's got to be absorbed, it's got to be readmitted, and it's like Domino Effect or something, okay? So I could say, oh, well, it went in at this speed, and it came out at the same speed. How does that happen? Has it got a motor or something? It comes in, it slows down, and then all of a sudden, it speeds up. It's something to think about, right? And when it comes off the atom, what speed does it come off the atom?
Fast.
Fast, speed of light, right? 0 time, that sucker gets up from 0 to the speed of light. No. It hurts my head. Okay?
So how fast
But
is light?
How fast is light? Light is fast enough, and I may get my number wrong, but you can look it up, okay? That it takes something like 8 minutes to get from the sun to the earth. So if the sun went out by some magic, right? Then you would have 8 minutes before you knew it. Okay?
So when you see a sunset, actually sunsets happen 8 minutes before.
But there's more to a sunset than that, right? Because here you are down on the earth, right? You're like like fish swim underwater.
Yeah.
You swim under this ocean of air, right? But it's real easy to swim through. So you're walking around on the bottom of this ocean of air, right? Well, air slows down light. And the thicker the air, the more it slows it down. Okay? So here you are underneath this little ocean of air. And here comes the light from the sun at sunset, right? And it hits this thing right here, and it starts to slow down. And as it slows down, it curves downward. Well, what happened to you? You want to know what happened to you? When you were a little baby, your parents thought so much of you. They wanted you to be smart, they wanted you to be beautiful, and you turned out all those things are just the way they wanted, but they helped that along, right? They put little dangly things over your bed, right? They played games with you with your hands, and they'd give you stuff, right? And you learned, without knowing it, what arm's reach means, right? So if you took a quarter, I don't have a quarter. Yes, I do. I have a quarter. If you took a quarter and hold it in your fingers like this and hold it out at arm's reach, as far as you can stretch it out, and look at it straight on, gauge its size. What size is it? You don't have to tell me. I mean, it wouldn't make any sense to me. But to you, what size does it look like, right? Now, would you come up here and stand up here? Here, I can hold you. Okay. All right. Now, hold it out arm's length, gauge its size, okay? Now, put it straight over your head and look up. Gauge its size now.
It's a bit bigger.
It's a little bit bigger?
It's big.
You think? Okay, you were not tricked as a baby. Okay? Some people get tricked as a baby. And here's what happens. There's arm's reach, right? And they see the size of the quarter. You older folks can try it. It's interesting. And now look at the distance from my eye to that quarter, right? What happens when I do this? What's the distance now from my eye to the quarter?
It's actually less.
It's actually a less distance, right? Which means the quarter is going to look to the what can I call it? Unprejudiced eye. The quarter is going to look to the unprejudiced eye to be bigger, just like you did. You found out, right? But to the prejudiced eye, like my own, it looks the same size because I've gotten so used to arm's length is that far away. And it depends on what happens to you as a baby. So, good job, Dad, Mom.
Oh, thanks.
There you go.
I don't think it's right. Oh, cool.
Thank him.
Split it with me later.
Okay. All right. So, you know, where are we now? We're more in terms of what it does. So if I set this up so that I could isolate, you know, you take it, you get in your mind, I want to isolate a beam of light. You know, I want to squeeze it down to just a real sharp point. So I've got a laser point there, and I can't get rid of all the light, but we can get rid of most of it. We can get rid of some of it. So if you look at the screen here, it's going through the slit, and I'm going to, as carefully as I can, I'm going to narrow down on that. I'm shutting the slit, hoping to isolate the beam of light. And look what I do to it. It's dimmer because there's less light going through the little crack, but now it's spreading, and the further down I go, the more it spreads until I can't see it anymore. So what causes that? You know, oh, it's a wave. waves do that. So it must be a wave. No, no. Waves do that, and that does that, so I can explain that behavior with a wave model. Everything is a model. Now, that's a nice, clean little blur. Okay? But if I open the slit again and get rid of that blur, and then take two slits, now what happens? I've broken it up into, if you got up real close, you could see a bright spot, and then in between a few more little bright spots, and in between a few more little bright spots. And that's a combination of what they call single slit diffraction and double slit diffraction. So it's not only spreading it, it's breaking it up into these little strips. Now these little dark places represent what you see when you look through your squeezed fingers, when those hairs sticking down. So what you're looking at between your squeezed fingers is light, dark, light, dark, light, dark. Okay? So let me wrap up by saying, going way out on a limb, you do not see light. You think you see light, but you don't really see light. You interact with light. There's light here. There is light here, right? I see it against this thing, and I see it against this thing, but only because it's hitting and bouncing back. And it's going directly into my eye. Now think about how small that little hole is. And think about what happens when you go in bright light and it gets really small. And suppose you have trouble seeing. Try sometimes taking a page without your glasses and finding a letter and taking your fingers like this and making a little hole in your fingers, squeezing it together, and then look at the letter. And you'll find almost magically it looks like it magnifies. But what's happening is you have better acuity. So as your pupil closes in, you get better acuity, but you get less light. You don't receive as much. And so, but try that sometimes. Okay, so the only way to see it is to put something in its way so that it reflects off of it. And if I take this dragon here, you can see the light as it bounces off the different bubbles of glass that make up the dragon. And I can also shift it . I think I can shift it. Maybe I can't shift it. Okay, I take that back. I'll think about that another day. Okay, let me speculate. I mean, really speculate. I think we are about to embark on a whole new era in science. And my vision is that we are going to see space for the first time probably as no thing, not nothing. Space may be no thing, but space has characteristics. And one of the characteristics of space is that electrons accelerated can evoke electric and magnetic fields in space. The only point being, you get the illusion of speed if something pops up here and then it and then something pops up here, and something pops up here, and this one starts reducing, and these start rising. And if you had a whole string of these popping up and reducing, popping up and reducing, you would get the illusion of a wave. So when an electron accelerates, a magnetic field is established around that electron at exactly right angles to its motion. That magnetic field, that changing magnetic field, creates a changing electric field right in front of it, which creates a changing magnetic field in the opposite direction right in front of that, which creates a changing electric field right in front of that, but downward, and that goes on forever. Now, does the wave travel? This is where I'm on a limb. I don't think there's any such thing as the wave traveling through space. I think these arise in space due to this effect, this cumulative, I can't even call it a cumulative effect, this interactive electric and magnetic effect. So I don't say the speed of light. I say the reactivity rate of space. Space reacts at this speed. I just made that up. Don't quote me. So that when an electron accelerates and the electromagnetic wave travels and the electromagnetic wave interacts with matter, it can kick out an electron. Where's the light? Right? So I can make up a story that eliminates light and have the effect travel as a wave and interact as a particle, because it's transferring momentum, it's a particle. It's moving through empty space. See, we have a trouble with waves because think of waves on water. Now take away the water. What's waving? They had this problem for over 100 years. They had to first imagine that space is filled with a phlegm. That was their first word. Then like, oh no, it's aether. A-E-T-H-E-R. So then they had objections to that, because if the world goes through the aether, there's going to be friction, we're going to slow down, we're going to, you know, go into the sun, something like that. Won't work. So should we stop here? Is this good enough? I hope you go away without many answers, but I hope you go away with a lot of questions and maybe some respect for how you evaluate your questions, how you evaluate the answers you get to your questions. I would suggest that you don't just read one book or listen to one person. You read a lot of books. You listen to more than one person. And you make up your own mind, okay? So I would encourage you to make up your own mind. But make sure it's got to be consistent, got to have predictability. You got to, you know, in other words, you wouldn't have survived it this far if you hadn't had predictability. It's got to be consistent, predictable. It's got to be reproducible. Somebody else has got to be able to do it. It has to make sense in terms of everything else. Good luck.